Welcome to The Explainer. Today, we are diving deep into Google's brand new Gemma 4 family of AI models. This is a huge step forward in making AI more accessible, more efficient, and, well, just plain better. Let's get into it. So, this is the big question in AI right now, isn't it? How do you create something powerful enough for massive, complex problems, but also efficient enough to run on the phone you're holding right now? In this explainer, we're going to explore how Google's Gemma 4 answers that question, all based on an absolutely brilliant visual guide from Martin Grutendorst. You see, Google's answer wasn't to build one single model to do everything. Instead, they built a family, a coordinated team of 4, each one tailored for a specific job. You've got the 31 billion parameter powerhouse for the really heavy lifting. Then there's the efficient giant, which perfectly balances power and speed. And for our everyday devices, you have the on-device wizard and the super lean compact multi-tool. But before we get to know each family member, we've got to look under the hood. There's some seriously clever engineering that they all share. This, right here, is the secret sauce. Okay, so at the heart of any modern language model is this thing called an attention mechanism. It's how the AI figures out which words are most important for understanding context. Gemma 4 plays a really smart game here. It mixes the raw power of global attention, which sees everything, with the incredible speed of local or sliding window attention, which just focuses on the recent stuff. So how does that sliding window actually work? Well, imagine reading a really long book, but you're looking through a tiny slot in a piece of paper. You only see a few words at a time, but as you read, the slot moves forward, and you kind of remember what came before. It's incredibly fast, but you can probably guess the downside, right? It's easy to lose the big picture. And this quote just hits the nail on the head. If you only use that sliding window, it's like a game of telephone. The further you get from the beginning of the sentence, the more distorted the original meaning can become. And that's why Gemma 4 is so smart. It weaves in these powerful global layers that can see the entire context, making sure nothing important gets lost in translation. Okay, but wait, we just said those global layers are powerful, but also super expensive to run, right? So how does Gemma 4 get that big picture understanding without grinding to a halt? Well, it uses 3 very, very clever tricks. Trick number 1 is called grouped query attention. Now stay with me here. Think of the model asking questions or queries about the text. Instead of every single question needing its own personal set of reference books or key value pairs, a whole group of them, 8 in this case, share one. It's like a research team sharing one library card. It's just way, way more efficient. Trick number 2 is one of those things that's so simple, it's genius. For those big, expensive global layers, the model basically says, you know what? The signpost pointing to the information and the information itself, let's just treat them as the same thing. And boom, just like that, you've cut the memory you need for that part in half. It's a huge saving. And the third trick is something called prop. To really get long sentences, a model needs to know the order of the words. What this technique does is brilliant. It only attaches that positioning info to the first quarter of the data. This lets the other 75% focus purely on the meaning of the words. It's a fantastic way to separate the where from the what, which is crucial for understanding long conversations. All right, so that's the engine. Powerful, efficient, and smart. But what really makes Gemma 4 feel like a leap forward is that all the models are multimodal right out of the box. We're not just talking about text anymore. These things can see and hear. Yep, they can see. So how does that work? An image gets broken down into a bunch of tiny 16 by 16 pixel squares, almost like visual words. Then a special vision transformer comes in and reads the sequence of patches, basically translating the picture into a language that the main AI can understand. Now, here's where it gets really cool. It's got this thing called a soft token budget. It means you can decide how much brain power to spend on any given image. Need to identify a tiny detail in a photo? Crank up the budget for super high resolution. Just need to get the gist of a video frame, use a lower budget, and save on speed. It's this incredible trade-off between detail and performance. And it doesn't stop with sight. The 2 smallest models in the family, the E2B and E4B, also have ears. They can process audio directly, which makes them absolutely perfect for on-device jobs like real-time speech recognition and translation right on your phone. So let's recap. We've got this shared foundation of super efficient attention and the ability to see and hear. Now, let's see how that foundation supports our 4 distinct family members, each with its own special trick for its specific role. To really get what makes them different, you gotta understand 2 key ideas. The first is active parameters. Think of this like having a massive team of experts on call, but you only ring up the exact specialists you need for a job. The second idea is effective parameters. This is more like having a small, super fast model, but giving it a giant cheat sheet to look things up on when it gets stuck. So let's start with the 26B model. It uses that first approach, the mixture of experts. It has a staggering 26 billion parameters in total. But, and here's the genius part, for any one task, a little router only fires up 4 billion of them, picking the best experts for the job. You get the performance of a giant model, but at a fraction of the cost. Now, the smaller E-models, the on-device wizards, use that second concept, per-layer embeddings. The core model that does all the hard work is tiny, so it can live in that fast, expensive memory. But at every single step, it can quickly look up extra info from a huge database stored in slower memory, like your phone's flash storage. It's like having a tiny, quick-witted brain with access to an entire library. And this slide just lays it all out perfectly. You've got the big, dense 31B model for when you need maximum firepower. You've got the incredibly efficient 26B mixture of experts model for high-end speed. And then the two E models using per-layer embeddings for amazing on-device performance. The big takeaway here is that there's a tailored solution for just about any hardware you can think of. So, okay, we've waded through all this clever engineering. But what does it all mean? What's the really crucial point to take away from all this? What Gemma 4 really shows us is a major strategic shift in AI. It's not about building one giant model to rule them all anymore. It's about designing a coordinated, efficient, multimodal family of models that gives you the right tool for the right job, whether that job is in a massive data center or right there in your pocket. It's AI built for the real world. And that leaves us with a really fascinating thought to chew on. Are we watching the end of the era of single, monolithic AI models? Maybe the future of AI isn't one giant, all-knowing brain, but something more like a whole collaborative family of them, each bringing its own unique strengths to the table. What do you think that means for the future?